So let's take a look at electric potential, which has the symbol V. And the units for electric potential are volts, and 1 volt is equal to 1 joule per coulomb. For whatever reason, we abbreviate volts with a capital V, which is the same symbol that we use to represent electric potential, so I can see that being kind of confusing, but you'll get used to that. And the importance of it being 1 joule per coulomb is something that we'll take advantage of and see more in the lecture right after this when we talk about electric potential energy. So I'll start with how it's similar to the electric field in that electric potential has a unique value at every point in space. Unlike the electric field, potential is not a vector, and that means that calculating the potential is usually easier than calculating the electric field. For a single point charge, Q, the electric potential at a certain point is equal to K times Q divided by R, where V is the electric potential at a point, say P, caused by Q. K is the constant, 9 times 10 to the 9. Q is the charge on Q in coulombs, and R is the distance, the straight line distance, from Q to P, and that would be measured in meters. You might notice that this is very similar to the expression for the magnitude of an electric field for a point charge, which is kq over r squared. And the main difference here is first that r is not squared on the bottom, but then also that this is a scalar quantity. There's no direction for potential. And again, that makes the math a lot easier when you have multiple point charges to consider. Now, what this also means is that potential can be positive or negative. So if the charge Q is positive, then the potential is going to be positive. And if the charge Q is negative, then the potential will also be negative. When there are multiple point charges, then the net potential at any given point is just the sum of the individual potential calculations. So mathematically, we just say V net is equal to sigma times Vi, so that's just the sum of the individual potential values. So if I now call Q Q1, and I still have point P, then I'll actually draw a distance R1 in between them, because soon I'm going to have Q2 and Q3 and so on. So when there's only one charge, we have exactly what we had before. We would just have V1, and I can expand that, and then I get K times Q1 over R1. And remember, it's not squared because this is actually the potential. It's not the magnitude of the electric field. Then if I add another charge, Q2, down here, R2 will go from Q2 to P. And R2 is the straight line distance, so that's always going to be positive as well. Then when I find Vp, I can just add V1 plus V2 to get the net potential at P. And so then when I expand V2, I have K times Q2 divided by R2. And this keeps going. If I have Q3 down here, then I get the straight line distance between them as R3, and I just keep adding. So the net potential at point P is V1 plus V2 plus V3. And when I expand V3, it's just K times Q3 over R3, and this can keep on going 4, 5, 6. Usually on an exam, you wouldn't have to do more than 3, maybe 4, because at some point it becomes an exercise in math instead of an exercise in understanding physics. So usually on a test or exam, you wouldn't have more than 3, maybe 4. For homework problems, though, of course, when you have all the time in the world, right, then that's when they tend to ask questions with a lot more things like this. But you can see that the math is pretty easy for this. We just add them up, and there are no vector components to consider. Yay. It's not necessarily that vectors are difficult, although they are before you understand them. Once you understand them well, then they're not difficult anymore. But using vectors, especially in 3D, gets really tedious when you have a whole bunch of different components to consider.